URL in the chat. So please visit that URL and enter what comes to your mind when you see or hear about machine learning. So it can be anything recent that you've actually you've seen or hear people say, or even on the television. So do actually write in, and this is actually a word cloud, cats or dog. Machine learning, yes. All right. AI educating machines. Yes. Math. Okay. Actually, machine learning, there's actually a lot of math as well, but not to worry. All right. So as you can see, we have actually several answers, AI being the biggest. So I suppose that all of you actually have a general idea that what you see, as well as cats and dogs, which is actually part of one of our examples later on. So now getting back, so for those who are coming in now, yes, we are actually beginning. We will be beginning our workshop. So now from the word cloud, I'm actually glad most of you actually gotten a core idea. So machine learning can be AI, cats and dogs, which is the examples that you see, and medical that I see a lot of examples that you actually put in there. So actually, to be more specific, machine learning is actually the development of computer systems that are able to learn for themselves without any explicit instructions. And by explicit instructions, more often than not, is given by the human being. So in today's world, I believe that many of you have heard about intelligent robots, self-driving cars, as well as many cool technologies that didn't really exist decades ago. So here, as you can see, let us take a brief look at the modern technologies of machine learning, so as to help us to appreciate the importance and widespread use of this particular technology. So first, we have security and surveillance. So it's mainly in the field of defense and homeland security. So using of facial recognition, behavioral detection methods to identify abnormal behaviors such as violence or theft or any crime in general in real time. So other than that, there's also the medical industry. So all this consists of medical imaging analysis, also through analyzing MRI, X-ray scans, and etc. And next, we actually have digital media intelligence, which I believe most of you are actually very familiar with. So this actually includes search engine optimization. So how it actually shows up what is most interesting to you, what caters to you the most, advertisement targeting, or recommend things that you most likely want to purchase based on what you've actually visited recently. So it might actually be a bit of invasion of privacy, but nevertheless, all this actually uses some form of machine learning and deep learning technology, as well as TikTok, which actually, if for those people that actually uses TikTok, so on your FYP itself, it actually shows the content that you're most interested in, and which is also what TikTok is best well known for. And finally, we have Siri, which is what the content which includes voice recognition and also processing, which is also known as natural language processing, which we will also be having a workshop on in the later date. So next, we have self-driving vehicles, which in recent years also is actually there's getting a lot of hype around it. So companies such as Tesla incorporate deep learning technologies in their vehicle that enables self-driving and route recognition. And finally, robotics and AI. So to appreciate machine learning, we will have to first look at how traditional programming works. So as you can see in traditional programming, it actually consists of two important inputs that the human would have to provide. So first, we'll give the rules as well as the data into the computer machine. So for the data itself, it will be as shown in the image of a girl walking, running, as well as cycling. So as for the rules itself, we will provide it to tell the computer how to handle or classify this data into different categories. And the rules can actually be known as your programming language. And for those who are not very familiar, I will explain what it means. So for example, in a hypothetical situation, if the speed of this girl is actually less than 4 kilometers per hour from the data, the computer will determine that she's walking. So if she's moving faster than 4 kilometers per hour, but less than 12 kilometers per hour, the computer will determine her to be running, and finally, if it's more than 12, it will be biking. So as expected, the computer will return us with a set of results based on this particular data, and the rules would we provide as shown here in the slide. So for those who are not very familiar with programming, this is a simple explanation of how traditional programming works. So there's quite a bit of human intervention needed, as you can see. So we would have to tell the computer what they should do, and then they would give us the result. So now let's flip things around. So instead of the example you have seen earlier, we have a similar computer machine here. But this time around, a particular computer machine is equipped with machine learning capabilities. So now, let us take a look at what are the differences between them. So instead of providing rules and data, we'll need to provide them with the data as well as the answers. So for the data, we have many different images of the cats, and they're all labeled respectively to show that it is a cat. So the images are the data, and the labels that you see are the answers, which is indicated there. So all this is actually passed into the computer machine equipped with machine learning capabilities. And then instead of returning us with the answers, as you have seen in the previous slide, the computer machine will return us with a set of rules. And having this set of rules, we will be able to identify distinct patterns and features in a cat image, which we can see its usefulness in the next slide for us to understand why. It is beneficial for us to do so. So here we can see images of the cats are being passed into the machine, and that is trained with the images of the cat. And by train, you can see it as the set of rules that you've seen in the previous slide. So this computer had determined from the data answers we have fed it with, and the answers. I'm sorry, apologies. So it is actually it's actually a set of rules that we fed into this particular machine, and that's why it's trained. So then we will pass the images of the cats into the machine as seen, all the different types of images, and the machine actually correctly identify it as a cat, as expected. But we see the last image itself, the machine failed to identify it as a cat. So why is it so? So this brings me to my next point. For machine learning itself is an ongoing process. So a good practice which you should always bear in mind is to always provide your machine or your model with sufficient amount of diverse data. So for instance, for our previous example that you saw, so we should always try to provide different orientation, colors, and breed of the cat images. So this will help us to improve the accuracy of the machine itself in general. And with more diverse data, we would have a greater accuracy. So now enough of me talking. I would like you guys to actually try it out. So we'll be sending a URL into the chat itself, if you all can see, or you can actually type it out in the URL. So once you're in there, you would actually see this Google Colab book that we have prepared for you guys. So for those who are facing any problems, do let us know. And also, for some of the participants, can I request you guys to turn on your camera, because we would like to take a picture of everyone in this workshop. Thank you so much for your participation. If you all can turn on your cameras. Right. Thank you so much. Yeah, you all guys don't have to be shy. All right, thank you. All right, in the meantime, for the rest of you guys, while you are also turning on your cameras, do also visit the Colab book, as if you all can see the link in the Zoom chat. So now allow me to continue now. So for the demonstration number 1, so it's actually this is an introduction. So we would just like to let you know, for this particular model, it's actually a pre-trained model that we have prepared for you guys. So the whole training of this actually took us 20 minutes. So for the initial setup itself, you can just press this tiny little play button here if you are following. For those who are not able to follow, not to worry, you can actually follow through by looking at this at the screen share first. So once you press the little play button, and then you actually start the setting up. So let me explain what all this setting up does. So for those who are actually not familiar with Python, not to worry. So I will actually simplify and allow you, most of you guys to understand what is actually going on. So for this section itself is actually importing of the libraries. So you can actually see it as obtaining the tools that you will need for the work that we are doing here. So these are actually known as libraries, which is getting the tools that we need. So as you can see, this wget, which is here, is actually downloading of the file. This file contains the model that we have already trained for you guys. So once it's actually downloaded, it is actually, then we will actually unpack it. So this cat_.dsc.zip. And then following that, we will load the model. So this is actually the framework that we use, known as TensorFlow. So TensorFlow is a framework for machine learning, which I will explain later on. But for now, it's actually one of the tools that we use for machine learning. So here we are actually loading the model. Once we unzip the file, and then now the setup is completed and the model is ready for use. So next, we actually look at the step 2 now, which is the upload of which is the fun part also. So you can press the play button and then it should load very fast. So now you actually point me to upload some images, and this particular machine will determine whether is it a cat or a dog. So for this, I've actually prepared a set of some images for you guys. So these images, the machine have never seen it before. So just a forward first. So all these are actually taken from Pixabay. So for those who are actually looking for images, you can actually search it here, pixabay.com. Okay, while it's loading. But yes, you can actually find it in Pixabay. So I'll upload these images as seen. I'll select it, then following that, I'll open. And then now it's actually uploading the images. So it does take a while. So as it is being uploaded in the same time, the image is actually being passed in the machine as you've seen in the slide itself. And then the machine will actually identify is it a cat or a dog. So in the meantime, I also do the same thing. I'll show you the code. For this is a little bit more complicated than the previous one. So because this is not the setting up, this is the actual learning, the machine learning process. But it's actually simplified a lot because the model itself have already been prepared by us. So this is basically the uploading of the cats and the dog. Then after that, we will upload the image here. And then this is one of the main portion here, which is predict. So this would actually predict the images. And then finally, it will come out with a set of results, a set of numbers. So all these numbers, we will explain what it means later on. So not to worry. And then this number will determine whether is it a cat or a dog. So as you can see, it actually correctly identifies it as a dog and a cat. So number 1 is a Labrador. Number 2 and 3 are the images of a cat that you've seen earlier on. But for those of you that actually go on to the website and upload certain images and the machine actually incorrectly identify, so this is what I mean as no machine is actually perfect. So all machine is constantly being trained, and this is the beauty of machine learning. So we have to keep providing it with data to make it improve, just like a human being. We are not perfect, but we are always constantly learning. So now let me get back to the slides. So for the next part of the slides, I hope the exercise earlier on is insightful in helping you to understand. So for those of you who are still doing the collect book, not to worry, you can actually, this link will actually be up all the way even until the end or after the end of the workshop. So after the end of the workshop, if you are still interested, do play around with it. So I hope this actually helps you understand what a machine learning can actually achieve. So the next segment, let's take a look at 2 different categories of machine learning. First, we have supervised learning, which is what you have seen in the exercise earlier on. And as supervised learning, I will be going into greater details in the subsequent slides. So for supervised learning, it is actually learning through the use of labeled data. And in the earlier slides that you have seen, we have a classical example of classification used in computer vision that's able to identify and distinguish the images between a cat and a dog. So as you can see, this is what you have seen in the example as well as the Google Colab book. So this is actually called computer vision. And another type of example here is actually regression. So I do hope that this word isn't unfamiliar for you, but if you're not familiar with it, not to worry. So if most of you actually remember back in high school or even secondary school, we have actually plotted graphs on paper using data points and told to draw a best fit line after our science experiment, for instance. So similarly, this is actually incorporating supervised learning with regression models such as this. And the computer will actually identify the most suitable data trend lines that would allow us to make accurate predictions and so much more. So you can see in the animation itself how the line is slowly being adjusted as the iteration. The iteration actually represents the number of times the machine is currently learned. It's actually running through how many times. So as it learns more and more, the iteration get higher, it's actually getting more and more accurate. So this is what it means as supervised learning for regression models. But what if we do not have enough data to train the machine? So I believe most of you or some of you will have this question might floated in your mind because we don't have every single data in the world today. So some data might not be available to the public, for instance. So how do we then create our own deep learning or machine learning model then? So here is where unsupervised learning comes into play. So the computer is mainly focused in discovering hidden patterns for unsupervised learning without human intervention. So we do not have to intervene too much since we are not required to label the data in order for the computer to learn it. So instead, the computer or the machine learning model will identify the distinct pattern on its own. And one very good example here is clustering. So for example, imagine you have a bag of different colored beans. So we have red, green, and yellow beans. So using unsupervised learning, we will be able to sort or classify them into the respective clusters based on the color. So which also happen to be the pattern here that the machine learning is actually identifying. So the image here is how the algorithm works when we try to visualize it. So now the next thing would be to actually take a look at the merits as well as the disadvantages of unsupervised learning. So as far as unsupervised learning is very useful, so it is actually indeed very useful. So it's helpful for finding useful insights from the data through the patterns that it detects in our data set. And the next thing would be how it closely imitates how human beings learn. So an example would be if you all guys remember when you were younger, I believe none of you actually remember, but when we were actually younger, we have this shape sorter toy. So for this shape sorter toy, when we play or how the toddler play, we can actually figure out what the shape is meant, which shape is meant to be for which hole without much explicit instructions, but through trial and error. So similarly for us, when we actually use unsupervised machine learning, how it actually does is it will keep on trying using trial and error to get a better result over time. Even though at the first time, we don't give it any indication and it makes a lot of mistakes, but eventually it will get better and better and give us our desired result. And the next thing would be on how it actually works on unlabeled and uncategorized data, which actually makes it so much more important. Because having so much data, imagine you have to label 10,000 amount of data sets and like images and all these would take a lot of manual work as well as expenses. So all these would require money as well as time. So unsupervised learning would actually save us from all this trouble. But at the same time, everything comes with a disadvantage as well. So this is the same thing for unsupervised learning. So for unsupervised learning, the results may be less accurate as compared to the supervised learning, which is the classification example that you've seen earlier. And also it's very time consuming, ironically, but the time consuming in this sense is actually during the learning phase, which we do not actually have to intervene, but it actually takes time for the machine to get used to and identify the distinct patterns in the data that we provide. So this is where it is time consuming. So the tools used in machine learning can be broadly classified into machine learning framework that will help us with the creation of our machine learning model. So remember earlier on when I mentioned TensorFlow, so this is actually TensorFlow as you can see here. And then apart from TensorFlow, there's also scikit-learn as well as PyTorch. All these are actually machine learning framework that is used by professional practitioners of machine learning all around the world today. And then next, we have the programming language that we use to create, or we use to communicate how do we want to build this particular machine learning model. So a way we can visualize this framework is like how a framework is like a toolbox. And then the programming language is like how we actually communicate the use of these tools to build the machine learning model. So how does machine learning exactly works then? So having been through the past 20 slides so far, I've yet to mention how it exactly works. So now I'll be exploring these questions in this particular section. So at the end of this section, I just hope that you understand these three key things. So first, neurons, neural layers, as well as network. Next is how neural network learn. And the third and the last point would be what is backpropagation and how does it work. So similarly, it might sound a bit unfamiliar for you guys, but do bear with me as I will explain them to you. So I wanted to show you guys about this artificial neural network called Trial and Error, this video, which I personally find it extremely helpful. So this video will actually show you, or actually help you see while it's an animation, but it will help you understand how artificial neural network works.
Liked learning on her own, through repetition and trial and error.
All right, so I do hope the video was actually helpful to further aid you in your understanding. So now I'll actually be using an analogy to further your understanding as well. So it will actually help you to familiarize yourself with the system before we actually dive further in. So imagine you have this handwritten image of a number 9 on the table, and your aim here is to determine if this number is 9 or not 9. I mean, of course, all of us here know what is the correct answer. So you proceed to actually show it to 3 of your friends. So Jack, Jordan, as well as Jane. So all of them actually have their own bias, so which we would have to account for as well. So all of them will actually form their opinion of whether this is this handwriting, is it a 9 or not a 9. So your friend, Jack, Jordan, and Jane, then proceed to whisper to 3 of their other friends, Alice, Tim, and Ken. So each of them similarly having their own set of bias. And finally, the last 3 friends we see here would then form a consensus as to whether that digit is 9 or not a 9 based on what they hear. And then once this consensus is formed, as we can see here, we will have a result. So assuming the answer is no, so the answer is that this handwriting is actually not 9. So what happened? So we will actually go backwards, and then we will tell them that the correct answer is 9. And then they will go back and then discuss to determine whose opinion is actually correct. So from there, the ones that say that it is not 9, the ones that actually mention that it is not 9, their opinion would hold much lesser weight. So in this case, it's actually Jordan. So Jordan actually said that it is not 9. So here we can see his weight, his opinion will actually hold a lighter weight, as compared to Jack, who actually gave the correct answer, which is 9. So now at least Tim and Ken would actually hold his opinion with greater regard. So they would then eventually form the correct consensus after each round of discussion until they get a correct consensus. So how and why is this analogy applicable then? So it is because from the analogy that you have seen earlier, the system behind machine learning is actually more or less similar to what you have seen here. But instead of having humans, we now have all these circles, each having a number. And all these circles you see here are known as neurons or node, which I'll be discussing now. So for neuron and node, as you see, each of these numbers in here that we see is actually known as activation. And then all these numbers actually represents a grayscale value of a particular pixel. And then also from the number itself from 0 to 1, so the lightest would be white color, 1, which is also known as being activated. And 0 will be the very dark color you see here. So this is how it will turn out being once it is being animated. So we have a grid of 28 times 28, and we have 784 pixels. And it will form all into a line into one single line into a collection of neurons, and we'll call it a neural layer. So I'll play it again. And as you can see here, this is the grayscale value of the pixel. And then they will all be lined up into a single line. And then this will form a neural layer. So what is then a neural layer? So for a neural layer itself is actually a collection of neurons and nodes operating together at the same column in a neural network, which I'll be talking about. So yes. So for neural network itself, it's actually a computer system model on the human brain. So it is actually made up of multiple neural layers as we've seen earlier on. So this is actually a human brain of a human brain neural network. So for this, as you can see, it actually consists of many small connections that we know as synapses. And all these will actually fire charges, electric charges, to communicate with each other that contains data and all this. But of course, I'm not a professional on this. But the point I'm trying to bring across here is this. As you can see here, machine learning neural network actually closely imitates how a human brain neural network actually is. And this is why machine learning model or machine learning neural network is actually inspired from how the human brain works. So for a neural network itself, it consists of 3 components. The first being the input layer. So the input layer can be seen as the earlier animated slides that you've seen, consists of a list of neurons and nodes. And next we have the hidden layer, which is basically many layers here, similar neural layers here. And third, we have the output layer. So in this case, you see, for the output layer itself, we have from 1 to 9. So why is it 1 to 9? Is because 1 to 9 is the number of output that we would expect it to be. So instead of having whether is it not a 9 or a 9, here we are trying to determine whether this handwritten number is it 1, 2, all the way until 9. So there can be only one answer that we would desire, which is 9. Hence, we have 9 neurons in the output layer here. So once again, this is another animation. So we'll be passed into from the input to the hidden layer, and then finally to the output layer. And the output layer would actually give us the result. So do note that this particular neural network that you've seen have actually been trained. So all this passing, this passing of the information that you see and all this, not to worry, I will actually be talking more about it in the subsequent slides. So what is then in the hidden layer? Having known the input layer as well as the output layer. So as mentioned earlier on, this is what actually it looks like. And then behind the black box is actually consisting of similar neural layers. And I know many of you might have some question in mind now, but let's take a look at it first and understand the smaller components in the neural network before I come back to explain how and why it actually works. So you actually be passed from the input layer to the first hidden layer, and then to the second hidden layer, and then finally to the output layer. And then next, we will actually take a look at how all these different layers, as you've seen, how all these different layers actually interact with each other. So first, we have the weights. And all these weights actually control the signal or the strength of a connection between two neurons. And for those of you who remember my analogy, you can imagine them as being two human beings, and that line is actually the weight of the person's opinion, how much his opinion matters. So of course, the greater the weight, the more important it is in that sense, the more it actually affects the result. So next, we have the formula. So for some of you who are not very math inclined, not to worry, it's actually pretty simple to understand. So for the x value is actually as what you can see here. This is actually the x value. So this is actually calculated by this particular formula here. So the f here is actually known as activation function. So for activation function, I will actually be going through later on. So for now, you can just take it as an alphabet F. Next, you have this particular portion here you see here, which is A1 multiplied by W1 plus A2 multiplied by W2, all the way until AX multiplied by WX. And all this is simply 0.2. Hold on a second. All this is simply can be calculated using this. So 0.2 multiplied by 0.7 plus 0.8, the activation number of the previous layer of neuron multiplied by this particular weight, and then 0.35 multiplied by 0.3, and 0.09 multiplied by 0.57. So some of you would wonder, how come we have all these number coming out of nowhere, like all these weights, or where did all these weights, all these number come from? So when we first actually run a machine learning model for the very first time, assuming it's not trained and all, so we are just running through the very first time, all these weights are actually just random numbers. And all these weight numbers doesn't actually mean anything until we slowly train it over time. And that is where we actually get the correct answer. Just like the analogy you've seen. So then after which we'll add the bias. And this bias is similar, once again, similar to the analogy I gave earlier on. This bias, but instead of a human bias, now this bias is actually an algorithm bias that is produced due to the assumptions made during the whole machine learning process. And x is the value. So in short, x is actually the value we get after passing in the sum of the product of each respective neuron activation and its weight into the activation function. And this brings me to the next slide. So finding and optimizing the correct weight value for each of the channel, which is these lines that you see here, is our main aim in machine learning. So, as mentioned previously, now I'll be talking about the activation function. So for activation function, it might sound a bit complicated, but for me, when I first started learning, I also couldn't understand what activation function is. But to simplify things for all of you, so we can assume that the red and blue circles are items we are trying to classify here. So using activation function is to actually introduce non-linearity to help our machine learning model to learn complex patterns, as not all patterns are linear. So for example, as seen here, assuming you are trying to classify, or we're trying to separate between the red as well as the blue circles. So using a linear function alone, we would end up with something like this. So we will not be able to classify our data accurately. Instead, by using an activation function, we are able to use the non-linear function that's much more suitable and much more appropriate for classifying or separating our data, our different data points. So in short, that is actually what an activation function aims to do, which is to introduce non-linearity into your calculation. Next is actually the common type of activation functions. So for some of you who have never seen all this before, not to worry. So you do not have to remember or understand the math behind each and every activation function in this workshop. But this is actually to let you have an understanding that there is actually different activation functions you can use. And in the next slide, I'll explain why do we have so many different type of activation functions to choose from. And some of the common ones would be tangent hyperbolic, which is the first you see here. Next, we have the ReLU and the sigmoid, and then the linear. So linear is actually one of the activation function, but just that we need activation function for the non-linear. We need the non-linear functions to help us to have a more accurate calculation and computation in machine learning. So which activation function do we use then? So it depends on the problem type that we have here. So problem type can be broadly classified into two different categories that you can remember: classification as well as regression. So for classification is what you have seen earlier on, the cats and dogs and all this. And regression is what is another example that I've given to you earlier, which is the best fit line, drawing of a graph using data point, and that is regression. Next, classification can then be classified into three different types again. And once again, you do not have to remember all this because a simple Google search would actually get you what you actually need for a certain problem type. So not to worry. So for classification, let me talk about binary classification. So binary classification is either this or that. And by what I mean is classifying between cats and dogs images, for instance. Hence, it's called binary, 1 or 0. And then for multi-class classification, it's actually classifying a set of images of fruits, which can be oranges, apples, or pears. This is why it's multi-class. It's called multi-class classification. And finally, multi-label classification. So it's used in, for instance, classifying a list of movies into their genres, for instance. So movies such as Spider-Man No Way Home, for instance, can be classified or labeled as both action and adventure. So there are actually multiple labels to a single data. Hence, it's called multiple label classification. And finally, for regression, like what I've mentioned, it's just simple set of data points. And our main aim here is to find the best fitting line that will classify the data points accurately. As for the reason why behind each activation function is used for a specific classification, testing results by practitioners and mathematicians, math explanations is able to explain it. But due to our time constraint here in this workshop, it is not within the scope of this workshop. So for binary classification, we generally use sigmoid activation. Multi-class would be softmax activation, and multi-label would be sigmoid activation. And finally, for regression, we will be using linear activation in this case. So now we have learned about weights, activation function, and how each layer interacts with each other in the previous few slides. When we take a look now, let us take a look at the bigger picture. So the hidden layers are there to act as an intermediary computational layers. And by what I mean is, basically the same calculation that you have learned earlier on, this particular formula that you've learned, will go through an activation function and then produce an aggregated result in each neuron that can be passed as the output to the subsequent layers. So these will occur repeatedly from the input all the way to the output and finally giving us our result. So this is how all the different layers interact with each other when we put everything together. So you also probably wonder, why 2 hidden layers? And why the number of neurons in each layer? So I would actually have to say, if you ask anyone, deep learning or machine learning is a combination of art and science, ironically. So as far as a lot of people actually see as math, which I remember when I actually asked what machine learning means, one of your guys actually mentioned about math. So yes, it's actually math, but at the same time, deep learning is also an art. So the number of layers and neurons chosen in hidden layers are actually arbitrary. And by what I mean is, there isn't a specific number that you have to follow or a specific guideline that there isn't a specific number that you would have to follow for a particular problem type. But instead, it requires you to keep on fine-tuning and testing until you find the right number of best training result. And if some of you guys are confused now, in one of the activity you will see later on, you will actually get to try out yourself. So now, before we begin on the activity that I've mentioned, so now let us take a look at this. So we will actually be sending another link in the Zoom chat. So you can go and visit this link and you will see something like this. So for this particular website that you see here, you just simply draw your number here. So remember the handwriting examples that I gave you. So now you are actually the one writing the hand, you are the one giving the handwriting, which is the data. So here, assuming I write a number 2, you would actually see that the machine can actually, not the machine, sorry, but the website itself actually can identify it correctly as the number 2. All this can't possibly be hard-coded, meaning you can't actually create a website that can actually read all these without the use of machine learning or deep learning. So this website have actually incorporated machine learning or a model within itself. So whenever we write a handwriting here, it will actually show us the results or the answers. So here you see, this is actually the input layer. And all this weighted value and all this is actually the calculation that I've shown you earlier on. And next is actually the hidden layer. Hidden layer 1. So here you actually see a tangent hyperbolic, you can see on your screen, on my screen right now. So this tangent hyperbolic is the activation function that I've mentioned earlier on. And then the output here that you see is the calculated activation number for each of these. You can see all this as neurons. And then it will go up to the next layer. And you can see all these different layers are actually affected by the previous layer. And all this calculation would then have an impact on the final result, which is the output layer. So for the output layer here, you can see 0.98, which is the max, which means that it is most likely that this is the correct answer as compared to, you see, for instance, 3 is negative 1.04, 0.95, negative, which all is actually very small. So 2 give us the highest number, which means that the machine has determined that it is most likely to be the number for this particular handwriting. So instead, now let me show you another example. Instead now, if I were to draw a number 1, here you see that the machine actually gave me the wrong answer. So it actually gave me a 0 instead of the number 2. I'm sorry, instead of a number 1. So the reason why is because, as mentioned, so there can actually be flaws within neural network itself, as this is a very basic neural network. But when we actually introduce a more how can I put this? A more sophisticated or more useful technique, which we call convolutional neural network, into our neural network system, it will actually improve the accuracy, which my partner Charlton will be showing you later on. But other than that, actually, once you try the different numbers, sometimes it works, sometimes it doesn't. But it depends on your handwriting and whether it is actually legible for the machine to see. So now let me get back. So how does a neural network learn? So a neural network, for a trained neural network, can actually be seen here. Once a neural network is actually trained, we would actually see a set of numbers, and you can actually see it as probabilities. So what I mean by that is, so for instance here, you see the different numbers, or even as seen in the exercise that you've played around with, the 3D visualization, 0.75 is actually the highest, which means this is most likely the answer, which happens to be as well, which is also correct. So this is expected because we have already trained the neural network to help us to correctly identify the different handwriting. So this is assuming that from 2 to 8, it is all less than 0.5. So the highest number here is number 9. So the output would be 9. But what about untrained neural network then? So here the network is running for the first time. So it is just making a random guess. Remember when I mentioned about the weights, all these numbers doesn't mean anything. This is what I mean. Since it is actually just making a random guess, the weights are all just random numbers in the first run. So as a result, it'll give us random numbers. And all this would actually mean nothing. It's not useful for us. Why would we even need it? but it is actually very useful. So in this case, the highest probability here is 0.81, which is the number here happens to be wrong. And it is expected because this is the first time we are running this particular neural network. So how can we improve it then? So here is an animation of how it actually works. So we pass it from the input layer to the first hidden layer, second hidden layer, and finally we get an output, which as mentioned here is actually utter trash. Because there is no way that we will actually find any use for this if we can't even identify a number 3. So this is where actually I'll be sharing with you how machine learning improves itself, or how does deep learning works to improve itself, or a computer improve itself. So now we have an actual value, which is a set of values you see. All these values are random numbers that is useless. Next, we have the expected number. For the expected number, we have 1 to 9 similarly. And for that, you see for the number 9, we have a 1 which is certain. So we are very certain that it is 9, assuming that here we are actually passing in the number 9 into the input layer. So once you are passing it in, of course, the probability here, that is the expected value. And this you can see as the answer, which is why we provide the answer to the machine during our learning phase. So how does it improve itself? So for machine learning, it mainly uses cause and loss function. And cause and loss function is actually a technique we use to measure the performance or the correctness of our algorithm or machine learning model. So as you can see in this particular expression, so this is actually known as mean square error. So this is one type of cause loss function that we can use. But for simplicity for this particular workshop, we actually chose this as it is the easiest to understand. So the square itself is simply to remove any negative value. And the actual minus expected is to simply find the differences between the two. So how we quantify the differences in the expected versus actual results? So first, we have the actual and expected here. So one is the one that is basically useless for us, and the expected result is what we want. So we actually do the math, all the form using the expression you've seen earlier on, and then we actually get a set of numbers here. And we will sum all of these numbers up, and it will give us a cause and loss value. And this value is extremely useful. So because this cause and loss value in training itself of a neural network, our aim is to actually minimize the cause and the loss value to as close to 0. So the closer to 0 it is, the better our results get, which means our neural layer is actually much more accurate now. So how is it actually achieved? It's actually through repeated trainings over neural network with different data. So this is known as backpropagation. And now I will bring back to my analogy once again. Remember when I mentioned that once we actually tell them whether is it a 9 or not a 9, we go back to that friends again and we tell them that your answer is actually correct. Your answer is actually wrong, assuming that their initial answer was not 9. So since their answer is wrong, this is where when we bring it to the context of machine learning, backpropagation simply means going back, where we are telling the computer its mistakes and what should it do to readjust for a better outcome here. So we cannot change the activation of the neurons directly. The only variables here are the weights as well as the bias, which is the lines and channels that you see here. So you actually adjust accordingly, and the degree of adjustment is based on how much we need to decrease or how much we need to increase it to get the lowest cause or loss value. So why is it called backpropagation? So in short, for backpropagation is simply like what I've mentioned earlier on. The neurons itself will actually fire back to the previous layer of neurons to readjust the weights and the bias of each connection such that the loss is minimized. And then if there is more than one layer, the same thing will happen for each layer until it reaches all the way until the input layer. And then due to time constraint and the amount of information we need to cover in this workshop, if you're interested to find out the math behind as to how neural network learn to improve itself, please visit this URL, which contains a document that we've prepared for you. So in there, we've included a more technical explanation of the behavior and how it actually works. I would highly recommend you guys to take a look at it, as it would help you to understand machine learning better. But for now, you can actually visit this particular URL after the workshop, and then you would have a more in-depth understanding of it. So finally, now let us take a look at this particular exercise on how it actually works for a neural network training exercise. So we actually be sending another URL here into the Zoom link, and you can actually access this particular website through the Zoom link. So for those who are following now, this is actually provided by TensorFlow, which is actually run by Google. So all this particular play button is simply to begin or to stop or to pause the training that we have. Epoch is simply running the number of iterates we are going through. So the number of times we are running through with our set of data. So imagine that we have 1,000 set of training data, which Charlton mentioned earlier, later on what it all means. So imagine we have a set of 1,000 images of cats and dogs. We are using it to train the machine. One epoch simply means running through 1,000 images over one time, and that forms one epoch. And this is being run repeatedly all the way until our training loss is actually minimized. So now we have the tangent. Here is the activation function, value, tangent hyperbolic, sigmoid, as well as linear. So this portion is actually the input that you've learned, as well as the hidden layer. And finally, we have the output layer here. The goal of this is to actually classify all these little dots you see here into its respective colors. So for instance, the orange color dots should go to the orange color zone, as well as the blue color background should only be within all these blue color dots. So let us run once to see how it actually looks. So as you can see, in a quick 159 epochs, we actually achieve it. It's actually pretty close to what we are looking for. We can actually run it. You can actually try running even longer, and then you will see that the training loss is actually getting lower and lower, which is expected. So this is where I would like to show you guys what weight actually does, how adjusting weight actually affects our output. So for instance, as you can see, all these are little features that you see. So instead of pixels and all, you can see all these input layers as the features of our input data. So here, we have all these different multiple features you see here. So assuming that for now, for this particular, the weight is negative 1.3. So now let us increase the weight to 5, for instance. So here you see, once we increase the weight itself, it actually gave us a pretty bad result, a pretty bad output. So it's actually totally out of the particular zone that we should be, our data point should be in. So this is how actually weight affects our data. However, if I actually turn it back again, if I actually lower it back again, then you will see that actually the output now is better. Do play around with this, as that would actually help you with your understanding. And then for hidden layer, you can also add the number of neurons. And you can see all the features, there are more and more features here. And then when you play it, you can see it's actually training. And you can also decrease it as well. But once you decrease it to a certain point, you'll realize that our training loss seems to have some issue here. It can't actually classify at certain points here. This is where we actually need more neurons as seen here. So you actually account for more features, and then it will give us our desired result. This is the reason why earlier on I said that there isn't a hard and fast rule on how many hidden layers you need or how many neurons you should put in. It is normally more about your testing data. And once you test it, what output you get, and whether the output is what you want. So if it isn't what you want, then you would actually fine-tune it and play around with the number of hidden layers and all to try to find out what is actually the best number of hidden layer or the number of neurons for your training model. And here you can add the number of layers, neural layers as well, and you'll see how the neural layer change, how the hidden layer features change. And for those who are more curious, you can actually simplify these. So you can actually add in, for instance, the number of hidden layers. So you can just refresh it. Then I can actually increase the number of hidden layers. Do play around with it, as it will help you to understand better how all these actually come together. So to summarize my portion, we will first take in an input and multiply by the neuron weight. Following that, we will add the bias, and then we will feed the result, which is X, to the activation function. And finally, we'll take the output and transmit to the next layer of neurons. And this is how, in short, each layer interacts with each other. So now, Charlton will be taking over me now. So we'll be sending in another URL here. So this particular URL is basically coding of a neural network, which Charlton will be going through with you. This is another activity which I believe would help you to understand how everything comes together.
Okay, hi. So hopefully you all can see my screen. So basically I'm Charlton and I'll be going through the second half of today's workshop. So while I'm presenting, please direct questions to Wei Pin because I can't really answer them while I am presenting. So please click on this link. The link should be sent in the Zoom chat as well, if I'm not wrong. Yeah, so after you click on this link, you should be able to access a Google Colab notebook that looks something like this. Yeah, so I'll give you all a while to type this into your chat. Okay, so the first thing you want to do once you actually reach this notebook is that there should be this button called copy to drive at the top left-hand corner. So the reason you want to do this is so that you have your own copy in your own Google Drive. That way, any changes you actually make will be saved to your own copy, because any changes you make in my copy won't be saved. So there should be a button somewhere about here. Alternatively, you can click File and click Save a Copy to Drive if you can't see the button. So without further ado, I'll continue to actually talk more about this code. So first things first, I'm sure you all saw the code earlier that Wei Pin showed. There was this thing called importing libraries. So just to reiterate what libraries are something like a pre-written code. So this code could have been written by, let's say, machine learning professionals or people who have like expertise in machine learning. So they can actually like help us code all these algorithms and help us code these neural networks that we don't have to recode and know the algorithms ourselves. So by simply importing libraries, this will allow us to actually use their functions that they coded for us without actually knowing how to code all the complicated math things behind this. So what you want to do is press this play button and this will actually run the cell. So throughout this notebook, this will be what we're doing. We'll just press this play button and we'll run the code cell, and you can see the first time you run, it will take a while because it needs to connect. So just click the play button and it should, once you see this green little check mark by the side, it means that the thing has finished running. So hopefully you all have finished running, but while letting it run, I'll move on to the next one first. So here we'll be doing a simple example predicting the y equals to x graph. So I'm sure many of you have seen this since you were like very young. So what we're trying to code here is that a model that given the x value will be able to predict the y value. So let's say we give the model the number 5. What we want our model to give us back is the y value, which is 5 in this case. So if we give the model the number 6, we want it to give us back the number 6. So that will be the first thing we'll be trying to do, a very basic example. So you can see here we've prepared some of our data. So in this data set, we have 4 values. We have 4 x values. So the first, in the x values here, you can see that we have 0, 1, 2, 3, and 4. And in the y values, these are the corresponding outputs that we want from our x values. We have y equals 0, which corresponds to the x equals 0, y equals 1, which is the answer we want when x equals 1, and so on and so forth. So this is the data set that we'll be training our model on. So this is what we'll be passing to our model and causing it to learn and come up with the y equals to x model that we want. So just run this cell, should be fairly fast. And this next cell is where it's quite a standard way of coding our machine learning model. So firstly, we have this sequential. Sequential is just how you start off your machine learning model. And you can see here that we have this thing called dense. So in this case, the dense layer is also similar to the neural layer that Wei Pin has mentioned earlier. It's simply all the rows of all the neurons. Alternatively, the dense layer can sometimes be called the fully connected layer, and we'll be seeing that phrase quite a bit later as well. So this is a model with one neural layer, which is just one column of all the neurons. And over here, you can see that we're passing in some parameters to our model. We have this thing called an optimizer that you've never heard before, and this thing called loss, which Wei Pin has quickly touched on. So now I'll be reiterating some of them very quickly. So as mentioned earlier, loss is a way to calculate how wrong our predictions are. Wei Pin earlier gave this example of the predicted minus actual squared, and that is similar to what we are using here, the mean square error. So mean square error is similar, is the actual value minus our value that is predicted, and then we are squaring it to get rid of the negatives. So what about optimizers? Optimizers are something like an algorithm to help us minimize loss. So what usually happens is in the loss function, we want to minimize loss because it's how wrong our models are. So we want to find the lowest point. So let's look at this graph. Imagine, let's say this is like a terrain, like some mountains. And you're trying to get to the lowest point because in loss, you're trying to get to the lowest point. So let's say you start off around here and you want to find your way down here. That's actually what optimizers do. These different colored balls represent different algorithms and different optimizers. So you can see that they actually make use of different algorithms. So what they do is they basically track how the loss is changing as they tweak the weights, and they'll slowly adjust their movement based on that. So you can see that different optimizers can reach different points at different paces. So for now, that is just a brief overview on what optimizers do. We won't really be going through the algorithm, but just trying to understand the concepts of what optimizers do. So after we went through optimizers and loss, now we'll move on to the next slide. So this is where we fit the model, also known as training the model. So this is where our model starts to learn from the data that we've given it. So you can see we are feeding the X values and the Y values to this model. And as earlier mentioned, there's this thing called epochs. So I'll quickly touch on what epochs are. So epochs are the number of times a data set is passed through a model, but using these words may be a bit difficult to understand. So maybe I'll use an example, an analogy. So let's say the model is us, students studying for an exam, and let's say our data set are like practice papers. So epochs is something like the number of times you do the practice paper and learn from the practice paper. So that is an analogy that I'll be using throughout this explanation. So you can see for now, we set an epoch to 25. And when we run this cell, you can see that in each epoch, the loss will continue to decrease. This means that our model is continuing to learn each time it visits our so-called practice paper, or in our case, this is called the data set. So after it's finished learning, we'll do a little prediction here to see how our model is doing. So we'll be predicting the number 7, and obviously the answer we want is the number 7. But you can see that our model actually gives us the value of 5.99, which is more than 1 off from the actual answer, which is actually quite huge. So when this happens, we usually want to go back to our machine learning model and see how we can improve our code. So I earlier touched on epochs. So you all can try experimenting with the number of epochs. Try changing this number of epochs to, let's say, different numbers. And each time, run this play button to train the model. And then run this play button to see how your model can actually change in value. So I'll go ahead and change this to, let's say, 200. So it's significantly more epochs. And let's run it. This will take a while longer, as you saw. And let's hope that it will be closer to 7 this time. And you can see that indeed it went a lot closer to 7. Previously it was 5.99 and now it's 6.8, which is a lot closer to 7 than we want. So clearly this will help us. By increasing number of epochs, we got a lot closer to the actual answer we want. But there's also another way, and a lot more reliable way to actually improve our accuracy. And that is actually adding data. So this is quite an important part of machine learning. It's quite crucial to actually add data, as it's quite a reliable way to improve our training process. So I'll just add 4 more values here. You can see I added 5, 6, 8, and 9. So what we want to do is run this cell. So we have our new data. And let's try training it on just 25 epochs again. You can see only 25 epochs. And when you run our prediction, you can see that our prediction actually got us to 6.99, which is extremely close to 7, even better than increasing the number of epochs that many times. So one thing I want to bring out here is actually it's very important for us to increase the amount of data that we have, and it's quite a reliable way for us to actually improve the accuracy of our model. So I mentioned earlier about epochs. So this may lead you to question, if increasing the number of epochs will increase our accuracy, can we just keep on increasing our number of epochs? So this actually leads to 2 problems. As you saw earlier, when we increased the epochs to 200, the model took a lot longer to run as compared to just 25 epochs. So that's the first problem. We may not always have the luxury of time. So the second problem is what we call overfitting. Increasing the number of epochs can lead to a common problem in machine learning called overfitting. So I'll bring back to the example of doing practice papers. So when you do practice papers, your goal is to try and score as high as you can on a practice paper. And once you score that high, you'll tell yourself you've learned everything you could from the practice paper. You are extremely prepared. So the same goes for our model. The model will try its best to achieve full marks for the training set that you've actually given it. But the problem here is when you start doing a practice paper, let's say 1,000 times, 2,000 times, sometimes you may not really be learning the answers anymore. You'll just be subconsciously memorizing all the answers and just regurgitating them without actually understanding what's going on. So this is quite similar to how a model is overfitted. So the more the model trains, it will actually try to force its way through all the data points. And by doing so, it will tell itself that it's actually achieved full marks on this data set per se, because it's managed to pass through all the data points. But on the right here, you can see that the ideal curve isn't actually to pass through all the data points. There is this X here that is not touching the data point. So that is actually what happens when we start overfitting. This happens when we start to train it on too much, and it becomes too well fit on only the training data. And you can see how this becomes a problem. So let's say we give it a data point that is never seen before, a X value at this point. You can see on the ideal curve, it should give us a value at about this green line. But when we see the overfitted curve at this same point, it will give us this red line, which is wrong and much higher than the answer that we actually want. So this is the problem for overfitting. It will give extremely good accuracy on data that is been trained on. But on data that is never seen before, such as this data point, it will actually give us an erroneous answer, which is not the answer that we want as compared to this best fit curve. So there's also this problem of underfitting while we're on this point. Underfitting is when your model is actually unable to capture the relationship between the Y and the X values. And this usually happens when, let's say, there's something wrong with the model you're trying to use. So let's say you are trying to mimic a curve in this case by actually using a model that is a straight line. In this case, no matter how you change this straight line, you'll never be able to give you the best fit curve that we want. So that is underfitting, the inability to capture the relationship between the Y and X values. So now that we've finished this example, let's move on to something a little bit more fun. You saw the handwritten digits example that we saw earlier, and now we're trying to see how it actually works in code instead of just seeing those 3D images. So just simply run this cell, and this cell will actually import the data set from online. So there's on some libraries are actually data sets that you can import. So after we import the library, import the data set, you can see here that there's actually a few things happening. What's happening here is you're splitting our data into different categories. So it is what we call the training, the testing, and the validation data. So what do these actually mean? So these three categories are actually fairly common in machine learning. So there is the training data, the validation, and testing, as I mentioned earlier. So I'll go back to the practice paper example to demonstrate what each of these data sets are actually for. So as earlier mentioned, training data is something like past year exam papers. You'll keep trying to do them, then you look at the answers, see how you went wrong, and try to learn from them. Then we move on to the validation data. So the validation data is something like mock exam papers. After you do a few sets of past year exam papers, you want to do some mock exam papers to assess how well you've been learning so far. The thing about these mock exam papers that is questions that are separate from these past year exam papers. So it's questions that the model wasn't previously trained on. So we know that it's a fairly accurate way to assess how well the model is doing. So what usually happens in one epoch is a model will actually do a bunch of do the past year exam papers and look through all the training data. And then you'll go to the validation data, which is to basically do a mock exam paper to assess how well it's doing. And this will give the accuracy score or a score in this mock exam paper. And using this score in this mock exam paper, you'll actually go back to the training data and continue to learn. So this process will actually just keep repeating for every epoch. You'll do a past year exam paper, assess how well it's been learning, and tweak how it's been learning, and then do past year exam papers again until all the epochs have finished running. So after all the epochs are done, this will actually bring us to the actual exam. So once you've done a lot of past year papers, you've done a lot of mock exam papers, this brings us to the final exam. So that is the test data, data that has never been seen before in any of the epochs to the model. So because this is data that is never seen before, this is actually the most reliable way to assess whether how well the model will do on in the wild, which is on data that it's never seen before. So similar to an actual exam, it's questions that you've never seen before in your whole preparation phase, and it's how you usually end up with your final grade. So it's the way that I wouldn't say most accurately, but it will end up being what will be given as the final grade to, let's say, this model as well. So that is the three categories, how these three categories are split and come into play when you try to train a machine. So now that we have our data, let's try and look at what our data looks like. So this is our training data. And for now, you just see a bunch of zeros, which is not very helpful. So let's just look at the first data point. This is the first data point. So let's click display. And you can see that there is a bunch of zeros still, but you can see that there are some numbers interspersed here and there. So this still looks a little bit difficult. So let's ask the computer, what do you see with this? So what this function does is it will tell us how this computer is actually interpreting these numbers. So you can see that this bunch of zeros with random numbers in between actually gives us this image, which to us, we can tell it looks like the number 4. So how does this actually work? So now I'll be bringing you through how computers actually see images and how they're actually able to tell what the images are. So computers actually look at images through what we call RGB values, red, green, and blue. And I'm sure that many of you have heard these terms before. So this is similar to in our art lessons, the primary colors. All the colors that the computer sees are actually made out of different intensities of RGB values. So I'll give you some examples here below. So the values for each RGB actually range from 0 to 255. 255 means like there is the maximum amount of red there is, and 0 means that there is no red at all. So you can see having red set to 255 and green and blue set to 0 just gives us a completely red pixel. And the same goes for the other colors. And over here, you can see that giving red 0, green 0, and blue 0 gives us a black, which means no color at all. And let's say we want to form a color that is somewhat gray. Then we need to find the combination of red, green, and blue. So it's about half of the maximum amount of red, half of the maximum amount of green, and half of the maximum amount of blue. That actually gives us this gray pixel. So all pixels can be made out of these three values, a mixture of red, green, and blue. But you can see here that there is actually only one value that we are using in this data. There is not the three values that I've talked about. So as mentioned earlier, Wei Pian actually quickly touched on this concept called grayscale. So similarly, we have the value 0 set to black and the value of 255 set to completely white, similar to the red, green, and blue that we went through earlier. So you can see here that there is a bunch of zeros, and this actually corresponds to this black background around. As you can see here, 0 means black. I can see that all these different values represent the white pixels in the center. So why we actually didn't use the three values of R, G, and B is because the color is not actually important in this case. So it doesn't matter if this number 4 is in green or in blue or in red color. What we want to see is the basic shape. So by actually just using this grayscale, we are able to still understand the important things from this image, while actually reducing the amount of data our model has to look through by 1/3. So this is quite important in machine learning, where we constantly try to decrease the amount of data we want to give to our model, so that it will save us a lot of computation time. So after you've seen our X values, let's take a look at what our Y value looks like. So our Y values are simply the correct labels for the different pictures. So you can see this is our first value, this is our first image, and the Y value that corresponds to it is the number 4. So this is our Y values, it's just the correct labels for each of the images. So over here, we'll be formatting our data. So this is sort of like the flattening phase where Wei Pian actually mentioned in one of his animations. Is taking all the pixels and then lining them up into one straight line. So this will be useful because we want to set it as a neural layer that we can pass through to our model later. So this cell is basically for us to visualize some of our images. You can see what we are dealing with in a sense. So you can just repeatedly run this cell to see what are some of the data points that we have. So let's say this is the number, this image is here, and the label on top is the correct answer. So it's just for us to see what we're dealing with. So you can just play with this for a bit, just keep running it, see what you can see and gather from this model. So after that, we actually want to do what we call normalization. So normalization is a fairly common thing in machine learning. It's basically expressing them as a fraction. So as you mentioned earlier in grayscale, all the values actually range from 0 to 255. So over here, we're dividing them by 255 so that we can actually transform the data to values between 0 and 1. So why we actually do this is to help the model to understand what is the minimum and maximum values of the data that they're actually dealing with. So this will help them make better sense of the data. And this will actually make computation easier and learning more accurate. But why is this useful? Maybe we'll use an analogy to see why this makes it more accurate. So let's say we have a student A and a student B. So student A scored 10 marks in a test and student B scored 20 marks in a test. And with just these numbers, you can't really tell like how different they are because in different contexts, they mean different things. Let's say the maximum score of the paper was 20. Then you can see here that 10 marks is actually only 50% as compared to student B who actually scored full marks, the highest possible in the entire exam. And you can see that the difference between these two is 50% of the total, which is quite a lot. And we want the model to know that this is quite a lot. As compared to if the maximum score was actually only 100, then student A will have scored 10% and student B will have scored 20%. Then the difference is only 10%, which in the grand scheme of things is not as important to the model. So this is kind of the message we want to give to our model, to actually know what is the context, the higher scores that you have to deal with, so that it will make the learning more efficient and make the computations easier. So this is a simple, please remember to run this. So this is just a print statement. It's just for us to see the data. It's not that important now. So now I'll be going through this part of the code. So this part of the code is very similar to what we saw initially. We have the sequential, which is basically how we try to initialize our model. And you can see here that we have a dense layer, and we this time have another dense layer. So this is a model with two dense layers, or fully connected layers, or earlier you heard it as neural layers. So this is our model for now. You can see here, there are two dense layers. So yeah, this is all fairly standard way of writing. So just the dense layer. If I run this, just simply run the cell. And here we'll be compiling it. So you can see here, there is the optimizer as we saw earlier. And this time you're using a loss function called sparse categorical cross entropy. We won't go into the math of how this works, but just take into account that we're trying to predict numbers here, and we're not trying to predict them as relative to each other. We're trying to predict them as categories. So what this loss function does is helps us calculate the loss in predicting categories. Because let's say we have the picture of a number 1. If a model predicts it as the number 5, it doesn't mean that it's any more accurate than a model that predicts it as the number 9, because we don't want to see the difference in the values. We want to see the difference in how they categorize them. So that is what this loss function does. So it's just for you to know that there are different loss functions for different models that are trying to actually do. So after we've compiled, we'll simply run this model.fit, which will train our model. We'll just train it on 20 epochs. And this will take quite a bit longer because the data is bigger than the data we had just now. So give it some time to run. It should still be fairly fast. And you can see here that there is actually this validation loss. And this is actually the loss on the validation data set. So as I mentioned, every time it runs through the epoch, it will run through the validation set and calculate how well it's doing using the loss. And there's also accuracy here. And this loss corresponds to the loss on the training data. But because validation data is never seen before in the training phase, we'll be looking at this more to assess how well our model is doing. So you can see that it's finished training, and simply run this cell to see the accuracy of your model. And you can see that our model has a 80% accuracy, which it may not be very high to you, but it's a reasonable accuracy considering we only trained for 20 epochs. So earlier there was a lot of animations that you may not have really understood. So let's see it in our real code. So you can see all of these numbers. It's something like a confidence score. So the first number is how confident the model thinks that the number is 0. The second one is how confident the model thinks it's number 1. And the third one is how confident the model thinks is the number 3. So you can see that each of these pictures has all these lists of confidence scores. And what our model actually does is that it will actually take the maximum value. So the number that has the highest score in this entire thing, that will be what our model will predict as the correct answer. So this is just for us to see some of the predictions our model has. And now comes the assessment part. So here is for us to actually visualize our predictions to see how well our model is doing. So simply run this cell and it will come up with an image. It will show you the predicted label. I think there's an error here. Oh, I think there's a problem here. Let me just run it a few more times here if it works. I think there is a problem with the data. Okay, but anyway, I'll try and look into this later. But basically what this is supposed to show is how the predicted and the actual values of the classes. I think there is an error that I will try and rectify after the workshop. But yeah, this is basically how we want to code our machine learning model. So now that we've seen how a machine learning model is actually created in code itself, let's take a look at another neural network that we've actually briefly mentioned. So it's called convolutional neural networks. And this is probably why most of you are here today, to actually help in the to learn more about computer vision. So convolutional neural networks, also known as CNNs, actually a type of neural network that's actually specialized in image recognition and also designed to specifically process pixel data. So we'll explain more on why this is more better suited to predict pixel data later. So don't be too frightened by this image first. It looks a bit daunting, but we'll go through each layer step by step later. So first we have what we call the convolutional layer. And this is usually paired with what we call a max pooling layer. Again, we'll go through this later. And then this pair is again repeated once again on the side here. So there is another convolutional layer and another max pooling layer. So this layer is then flattened, which is basically aligning it, changing it from just a square to just a whole neural column. And this will actually be connected to our first fully connected layer, also known as the dense layer that you saw earlier. And there'll be another fully connected layer at the end, which is also the dense layer. So before I touch on more about this, here is actually a visualization that will help us see better how this actually works. So the link is already sent in the Zoom chat, so you can quickly type this link into your URL bar, DSC conf handwriting. It should bring you to a website that is similar to the one before, but instead of just these two lines, you can see now we have a lot more. So simply write a number here, similar to before. And you can see how the layers actually come together to ultimately give us the prediction that is the number 2 at the top here. So I'll just quickly run through what this visualization actually shows you. So this is the first layer, the convolutional layer, the max pooling layer, followed by another convolutional layer, another max pooling layer, and the two fully connected layers that we talked about earlier. So yeah, we'll be going into how each layer works more later, but it's just for you to have a more better visual of what's actually happening. So why is there a need for convolution? So as earlier we saw just now, when we write the number 1 by the side, you can see that there is actually, this model actually gives us the number 5, and it's quite confused between a lot of numbers as well. So this is why there is a need for convolution. The problem with neural networks we have is that it's actually unable to account for the different positions of the target. So let's say we have these 4 cat pictures on the left. You can see that the cats are mainly located in the center of the image. So what happens in a conventional neural network is that it will tell the model that, hey, we should just trust and look more into these pixels in the green square in the center of the image, because that's where we are usually finding the cats. So after reading these different training cat data, we'll actually just rely more on this green square in the center. But when we give it an image where the cat is slightly to, let's say, the left, it will look at this green square where it's always trusted to find the cat and can't really be able to find the cat anymore. So this will tell you, hey, there is no cat in this picture, which is not what we want. This is wrong. We want an algorithm that will be able to predict not only find the cat, but find the cat in different positions in the picture as well. Because in photos, objects won't always be in the center of the image. So as you can see here, we previously saw that there was a number 1 written by the side. Let's try it for this model. And you can see that this model is actually a lot more confident as well in giving us the number 1. You can see that it's actually quite bright blue. And you can see that this shows that it's extremely confident there is a number 1, as compared to this, which just gives us the wrong answer outright. So that is the message I want to bring across, and to tell you why convolution is actually more suited to deal with images and pixel data as compared to traditional neural networks. So now I'll be touching on the different layers. So how does the convolutional layer actually work? So convolutional layers actually have what we call filters. And in filters, they actually perform calculations on different parts of the image. So let's say this green square is what we call a filter to detect cats. What actually happens is that it will actually perform calculations on different parts of the image to give us values like 1, 2, 240. And in the parts of the images where it's actually able to detect the cat, it'll give us a higher value such as 240, which is very near the cat, as you can see here. So that is the main function of filters. And these values, this entire grid here is what we call a feature map. The feature map is what happens after a filter is run through and calculated all the things on an image. So this is actually a new image in itself, as you saw in this 3D example. This convolutional layer is performed filter on these few pixels below. And all of this is what we call a feature map. And you can see that they form an image on it by itself. So this is just another GIF to help you understand better how these are calculated. So let's say you have a 3x3 filter. You look at the 3x3 part of the image, perform calculations, and give the value here. And you'll just repeat for the other parts of the image until it forms this 2x2 grid, which will be a new image to be passed on to later parts of the neural network. So now we have a bit of hands-on. You can see that there is this link which will basically help you see better how filters actually come into play. So the link should have been sent in a Zoom chat, and it's DSC filters hands-on. So it should bring you to a page like this. There is a cat on the left, and there is another cat on the right-hand side, but it's a bit different. So now I'll be giving you a run-through of how these filters actually work. So let's say on this right-hand side of the slides, you can see that I provided you some examples of filters. So we have a horizontal filter and a vertical filter. So what I've actually keyed in now is actually the horizontal filter. So what this horizontal filter tries to detect is that it tries to detect horizontal lines and horizontal edges. So you can see here, a lot of the horizontal lines in the cat image are actually becoming a lot more pronounced, a lot more obvious. You can see especially this platform that the cat is lying on is a horizontal line, and it's become a lot more obvious in this picture by the side. So that's actually what filters aim to do. It tries to actually extract the parts of the image that we want, such as this, extracting horizontal lines, and then it will be able to pass on to different parts of the different layers of the neural network, so that it will be better, it will learn better. So I'll perhaps key in the vertical one as well to show you how it's slightly different. So you can see here, horizontal lines like the platform the cat was lying on has disappeared a lot more because this is trying to detect vertical lines. And vertical lines like, for example, the cat's nose over here, which is a vertical line, has become a lot more pronounced. So these filters are actually very common ways for us to actually manipulate images. And it's also commonly used by a lot of photo editing softwares to actually change your image. So by simply changing these numbers, we can have different effects. So these numbers here are actually a filter for sharpening your image. So the numbers here will just simply modify your image into the end image that you want. So yeah, this is basically how filters work. But the example we've seen here mainly shows us horizontal lines and vertical lines. It seems a bit hard for us to imagine how we can actually detect eyes, noses, and faces just with these three numbers. So how do we exactly do it? So this brings me to explain about the hierarchical nature of filters. So there are different types of filters. There are lower level filters, which detect lower level features, which are harder to break down even furthermore. And there are higher level filters, which rely on these lower level features to actually detect the higher level features. So I'll use this example below, which will probably illustrate better what I'm trying to say. So let's say you have a lower level filter called an eyes filter, which will help us extract the eyes from an image. So you can see the eyes are at these two parts, and it then gives us this feature map with the eyes at these two locations, similar to this image. And let's say we have another lower level filter, which is the mouth filter. So you can see that there is a mouth at this point of the image, and we'll pass it to this feature map, which will tell us, hey, there is a mouth at this part of the image. So now we have two feature maps of these lower level filters. So now let's say we have a higher level filter, which is the filter to detect faces. So how this filter will actually detect the face is that it will look at the previous lower level features. So in this case, it will look at this feature map and see, oh, there are two eyes in these locations. And then you'll look at this lower level feature map and see, oh, there's a mouth in this location. So after that, you'll combine the information from these two lower level features to actually identify that this whole thing is actually a face. So to reiterate, these higher level filters will actually rely on lower level filters to actually detect more complicated and more complex parts of the image. So as we saw earlier, there's this thing called the max pooling layer. Over here, we call it the downsampling layer, but they mean the same, mean similar things. So what is this max pooling layer exactly? So in our images, actually, we have about 800 pixels per image. And given that we actually have a lot of images, this actually takes very long for our model to learn. So what we want to do is actually try our best to decrease the amount of information our model has to process. So this is where the max pooling layer comes in. So as you can see, it reduces the amount of information so that we can actually allow our model to compute them faster. And it also extracts the maximum value. So as you saw earlier, there was this filters that detects cats, and it gave, let's say, 230 at the center. So why you want to do this is to actually maintain the information while reducing the size. So let's take a look at this example here. Let's say this is a filter to detect cats as well. So there is a value of 112 here. Let's say that it's very likely that there is a cat in this position. So when we actually take the max value, so what max pooling layer does is it looks at the quadrants and then takes the max value. So in this quadrant, 20 was the biggest number, it becomes here. 30 will be grabbed out, 112 will be here, 37 comes here. So you can see we actually reduce the size of our training data by 1/4. And while doing so, you may be wondering, how will the photo know all this information now? So we've managed to extract the more important information, so which is this 112. So the computer will actually still know that there is probably a cat in the lower left quadrant. While it won't know exactly which quadrant anymore, it still maintains this important and valuable information for the model, while being able to reduce the amount of information it has to compute significantly. So that is why we have a max pooling layer. So now you may be wondering to yourself, why do we always take the maximum value? Well, there are also other ways that we can actually use pooling layers. So because max pooling layers will actually help extract the feature that you are trying to predict more, max pooling layers are actually significantly more used compared to these other pooling layers. Nonetheless, I'll go through them a bit as well so that you'll be familiar with them. So there is this average pooling layer. You can see at the bottom right here. Basically, for every 2x2 grid, it will take the average value and you'll be given to this new image. And the same happens for the other quadrants. So what average pooling layer is usually better for? It's usually better for detecting smoother features and for detecting smoother images. There's also minimum pooling layer, which is mainly used to extract more irrelevant features, which is not commonly done. So as mentioned earlier, max pooling layer is quite significantly more used compared to these other pooling layers. And similarly, minimum pooling layer, just as the name suggests, will basically take the minimum value of each of the quadrants, as you can see in this example. So now I'll just give a recap on the model that we've seen. So we have this convolutional layer where we've talked about, we'll use filters to actually extract important features. And then we have the max pooling layer. As you can see here, it'll actually decrease in size on the right, which will basically decrease the amount of information our model has to process. Then we'll pass it through another convolutional layer and another max pooling layer as we went through. Then After we have these images, it will be flattened to form a new layer in one column. And it will be and there will be two fully connected layers. And finally, it will give us the output at the end. So the model that was a bit more complex at the start has been slowly broken down into these different layers. And I hope that you understand them a bit more now. So now that we've seen how this model actually looks like, we'll be trying to see how it actually looks like in code now. So the link has been sent in the Zoom chat already, and it should lead you to another Google Colab notebook that looks something like this, analyzing sign language. So similarly, you want to go to File and click Save a Copy in your drive so that any changes you make will actually be saved to your own copy. Or there should be a button about here that says Copy to Drive as well. So in line with DSC's Tech-for-Good movement, we are trying to show you how you can actually use ML to actually help the community at large. So in this case, we'll be using sign language to actually show you how you can use ML to actually bridge the gap between us and the deaf community. Because a lot of people may not be very familiar with sign language, we can use ML to actually make a model that can look at the sign language image and give us what letter the deaf person is trying to say. So this will allow the deaf people to communicate with those who are not as familiar with sign language better and close the gap between our communities. So similarly, we always start off with importing the libraries at the start. And you want to just press this play button to actually import all of them. So the first time will take a while to actually import. So another thing for this specific thing is you want to click on this arrow and go to View Resources. Then over here, you want to go to Change Runtime Type. And you want to make sure that it says here GPU, because the amount of data we'll be dealing in this example is actually a lot more than previously. We want to have a GPU so that we can actually increase the amount of processing power we have and allow the code to run more quickly, because we don't really have the luxury of time now. So just make sure it's on GPU. If it's not, simply click on GPU and run the code cell again. Just run this again. So after importing the libraries, next thing you want to do is to import our data set. So this is what this line does. It imports our data set. So these are all just like to make sure we have the correct folder. So it's just to make sure we know where our data is. And then this line simply unzips the data. So just give it a while to unzip. And you can see below that this is just for us to get the folder path again. So yeah. So this next code cell is actually just for us to show. So our data set actually comes with some examples to show us what we are going to be dealing with. So it's just the different sign languages. So we can understand better what images we'll be dealing with. If you observe, there is some letters missing because those letters are represented by gestures and not still images. So that's why we're only dealing with a slightly fewer number of alphabets. So here we'll be just setting our training and testing data. And here we'll be converting it to actually an array, which will allow the model to actually learn more easily. So this is just more or less for us to understand, for us to keep track of the categories. So these are all the possible categories that we are trying to include. So we don't need to understand this chunk. This chunk is just for us to visualize our image. So simply press the play button and it will help you visualize some of the images that you'll be dealing with. So the image below is the data that will be fed into our model, and the number on top is simply that the alphabet on top is the correct label for this picture basically. So you can see here that this is a A, this is a N, this is a P, and etc. So you can just keep running this cell if you want to see different types of data that you'll actually be dealing with. So as mentioned earlier, this will be where we normalize our data. We'll be dividing it by 255. And we'll also be splitting it into our training data, our testing data, and our validation data as well. So these are all fairly common practices in the world of machine learning, and we'll just be doing it every time we are trying to actually train our model. So over here, this is not entirely important, but basically we are trying to make sure that it's of the correct shape. We want to make sure that they are still a 28 by 28 grid so that we can pass it to the convolutional layer, which will want to expect a 28 by 28 grid. And this is the more daunting part. It's basically our model. So if you look carefully, it's actually quite similar to a lot of the things that we've done previously. There's a sequential layer to actually initialize our model. And you can see here that it ends with the two fully connected layers, as we mentioned earlier. So you can see the last two are these two fully connected layers. And it's actually the same here. We have two fully connected layers. Now this actually just follows the same as our model. So you can see there's a convolutional layer here, followed by a max pooling layer. And then we have another pair of convolutional and max pooling layer, and another pair of convolutional and max pooling layer, similar to these pairs of convolutional and max pooling layers. So you can see here, we also have this layer called dropout, which won't be entirely relevant. You can read up more about it in your free time if you want. But it basically randomly deactivates some of the links between neurons. So this will actually help to decrease the chances of overfitting, but we won't really be going into that. So just remember to run this cell to actually compile your model. And here you can see the summary of your model, the convolutional and pooling layers, and the dense layers at the end with some dropout layers. So these are all fairly similar to earlier. We have the sparse categorical cross entropy as the same as earlier. And here we'll now be training our model. So this model will take a bit longer to actually run because the amount of data we have is significantly more. So this will take quite a while, but with the GPU, it should still take fairly fast. So that's why I had to have you make sure you're running on your GPU. So we'll just run on 25 epochs, and you can see it should run fairly fast. And you can see that it's now finished with 25 epochs. So over here, it's simply a graph for us to see how the loss and accuracy changes. So as you mentioned earlier, the objective of machine learning is actually trying to decrease the loss. So you can see as the number of epochs increases, our machine will try its best to decrease the loss. And as the loss tries to decrease, our accuracy will increase as a result. So let's try to actually see what our model has predicted. So this is basically for us to see what our predicted values are. So you can see we predicted a 6, a 5, etc. And it looks a bit hard to understand with just the numbers. So let's try and visualize our predictions here. Hopefully this should run correctly. And yeah, this runs correctly. So basically what we have here is a 5 by 5 grid. So the predicted is actually what your model has predicted. So if the values actually match, the predicted and the actual values are the same, it means that your model has predicted it correctly. And you can see here that all the pictures has actually been correctly predicted by our model. And if you want to actually have a more concrete number to actually peg to see how your model is doing, you can run this cell. And you can see here that our accuracy is actually 92%, which is very high. So that is actually what we say as like the true accuracy score of our model on data that is never seen before. So you can also just keep running this model, running this cell to see how your model performs on different images. If not, that is the end for our coding segment. And now we'll actually move on to the Kahoot quiz. So the winner of the Kahoot quiz will actually stand to get a $10 grapefruit voucher. So yeah, please try your best and hopefully you'll be able to win a grapefruit voucher. Where is that? How do I? Hey, sorry, I can't have the Kahoot. I'm trying to get the Kahoot music to play. Don't know why the Kahoot music doesn't want to play. Okay, I'll give you all like maybe 1 more minute to join before we start. Yes, sleepy. Sorry, I can't get the music to play. I want the music too. Okay, we'll start. Is there anyone else who hasn't joined? Just type in the chat if you haven't like joined the Kahoot yet. Okay, I'll give like 10 more seconds. Okay, I think we'll just start now. Sorry about the music. I don't know why the music is not playing. Okay, but we'll just start first. Hopefully the music will join us along the way. Oh, I think I can hear the song now. Okay. Within
All right.
wanna...
Yeah. So for the rules and data, the reason why some of them got wrong because it's actually some of the trick question. So rules and data is actually for traditional machine, the traditional programming. So it is not for machine learning. For machine learning, we'll feed in answers as well as the data.
Okay, let's move on. Who's at the top? Oh, Celeste is at the top of the leaderboard for now. Let's see how this progresses.
So how do we measure the performance or the correctness of our machine learning? All right, so most of you, some of you actually put weights. So for weights, it actually measures the signal, the strength of it measures the strength between two neurons. As for cause and loss function, it actually is the one that measures the performance or the correctness of our machine learning results.
Let's move on. And now aim is at the top. Let's see how this continues to change.
What is a neural net?
It should be 100% hopefully.
Okay, so for this, we have a computer algorithm. So I understand why some of you chose computer algorithm, but neural network actually isn't a computer algorithm. It's a computer system model on the human brain. So remember the synapse example that I gave? So it is similar to that. It's neural network is actually modeled on human brain. And network in our brain is also not correct because for that is actually it's a totally completely different thing. Yeah.
Okay, let's move. Let's see who's at the top. Now Sleepy is somehow winning while being sleepy. Move on. What is weight?
What is weight? Do read it carefully. Alright, so two of you guys actually choose differences in bias between two nodes. So there isn't really such thing. So the weight doesn't actually calculate the differences in bias between two nodes. Instead, as mentioned, it is actually control the signal or the strength of connection between two neurons. Yep.
Okay, let's use at the top now. And it's now aim has overtaken sleepy. Let's see.
Bias is the phenomenon of observing results that are consistently prejudiced due to faulty assumptions. Need to be relatively simple, I guess. Okay. So, so it's actually true, because indeed for bias itself, it's actually a phenomenon where it's due to the computer algorithm during the machine learning process. There is faulty assumptions made. So as a result, during our calculation, or as you've seen in the formula earlier on, we do have to account for this particular bias. Yep.
Okay, let's see who is winning. And now Celeste has somehow overtaken and become on top. Let's see how this changes.
The main structural components of a neural net. Do read this carefully. Alright, so majority of you actually chose the correct one, and actually 5 of you actually chose output, input, hidden layer, as well as bias. So for that itself, bias actually isn't a layer. So bias, as mentioned, is actually the assumption, which is the faulty, we are accounting for the faulty assumption in the computer algorithm. So it is actually not a layer. So the layer consists of 3: input, output, as well as the hidden layer.
And Celeste is still on top.
Wow. What does an activation function do? Alright, so 5 of you guys actually, to be frank, when I created this question, yes, it's expected that most of you will actually choose the green color one, but it actually not just apply a math formula or math formula is actually what it does, but the intention behind having an activation function, what it actually do is actually it calculates a neuron whether it should be activated or not. And then you also introduce non-linearity, which if you remember that in the example itself, to separate between the red and blue color dots, what we do is actually we need this non-linearity in the activation function to separate them and give us a suitable, to ensure, to give us a more suitable and accurate result in machine learning.
Okay, let's see who's leading. And now Isin is on top.
How many types of machine learning are there? How many categories?
Based on our earlier step.
Alright, so also majority of you chose the correct answer, which is 2. So for those who have 3, maybe you guys have confused something, got confused with something else. So the main 2 types of machine learning is the unsupervised learning as well as the supervised learning. These are the 2 categories that we went through. Yep.
And Isin is still leading the charts.
Which of the following is not a common category for our data?
You all should get this. Yes, okay, most of y'all got the correct answer. So as previously mentioned, the 3 types are training, testing, and validation data. Isin still in the lead. Which of the following is a valid RGB value for a pixel? Okay, yeah, I think my questions are a lot easier. So you can see here that the RGB values, basically the numbers must be between 0 and 255. So the four of y'all who chose this 257 is more than 255. So that's not what we want. So let's move on. And Isin is still in the lead. What are CNNs supposed to be better than neural networks at? Okay, yeah, this is really fairly straightforward. I'm glad that most of you got it right. So it's to do with image data and pixel data. And Isin seems to have a steady lead. What do we call the output after we apply a filter? But I think I use this sometimes. So yeah, this is just, I mentioned it quite a few times basically. So it's a feature map. So what happens is a filter will do calculations on an image and the output will actually be called a feature map. And Isin is just extending her lead at the top. Which of the following is the purpose of a pooling layer? So for those of you who chose detect specific features, this is actually what we call the convolutional layer. The pooling layer is where we try to reduce the amount of pixels we have. So by reducing the number of pixels, it will decrease the computation time taken for our model. Oh, we got a question wrong. And AIM is catching up. Will she catch up? Which of the following can help improve the accuracy of your model? I have two answers here, so your few things first. Okay, so I have two answers, and I mentioned both of them earlier: increasing the number of epochs and increasing the amount of training data. And this is a final question, so it's gonna be a battle for first. Oh, is this a true or false? Does normalization involve rescaling the values such that they are within 0 and 1? Fastest fingers. I guess we'll see who's the winner. Yes, good job to all of you. So basically normalization is where we divide by usually 255 in our case, to actually make sure that all the values are within 0 and 1. So let's see who are our winners. In third place, we have
AJ.
Second, we have AIM. And in first place, we have So can the top player Isin send us what?
Yeah.
So can Isin send us an email so that you can send her a $10 Grab food voucher?
Have to reach us out, either one of us.
If not, thanks. That comes to the end of our workshop. So that's the end of our Kahoot.
All right. Thank you so much, everyone, for staying and participating in this workshop.
So just a reminder, we also have a fireside chat that's happening tomorrow and a workshop that's happening next week as well about natural language processing. If not, that is the end of our workshop, and thank you so much for coming.